So today we're going to learn about section 6.4 and finish up 6.5. We're going to first learn about enthalpy of reactions. This is a new word, enthalpy. And this enthalpy, the symbol is H, and it represents heat. And we talk about delta H. And remember, just like in the last thing about calorimetry, delta means the change in. It means final minus initial. So delta H for a reaction would be the heat of formation of products minus the heat of formation of reactants. And that would be because final, the products are where we end up. That would be our final conditions. And the reactants would be our initial conditions. So we have our final conditions minus our initial conditions. This symbol here means the sum of. It's a Greek letter S. You don't have to worry about it yet. This is just an equation. We're not even going to use it for today, for the rest of this lecture. I'm just introducing the concept to you. We will learn about it next time. The key, though, is we do have these heats of reaction. This is the symbol for heat of reaction, delta H reaction. And this little zero here, the knot up in the top, these little knots up here, those represent standard conditions. And for thermochemistry, when we're talking about heat, standard conditions are 25 degrees Celsius and 1 atmosphere. It's a little different from our PV equals nRT, where the standard temperature was 0 Celsius. For heat, standard temperature is 25 degrees Celsius. And the delta HF values, these values here, you look these up in tables. And here's some information about those. Heats of formation, we call this the standard heat of formation. The values are measured values. And the standard heat of formation is defined as 0 for pure elements in their standard states at 25 degrees Celsius. For any chemical that's not a pure element in its standard state at 25 degrees Celsius, the heat of formation value is actually measured using a calorimeter. And it's measured with a calorimeter, and the values are relative to pure elements. So enthalpy, this enthalpy symbol, we say it's a relative scale, relative to pure elements, this definition right here, being defined as 0 when the pure elements are in their standard states. Again, we will learn more about this in a later section. And we have some new terminology. You'll have to be familiar with these words. Exothermic, exit, therm, heat. That means heat is exiting, heat is given off as a product. Okay, so heat's exiting the reactants, it's being given off. Endothermic, so N like enter, therm, heat. Heat is entering. So heat would be a reactant. Some other vocabulary that you'll often see, heat is absorbed, heat is used. Anytime you see the words heat is a reactant or absorbed or used, that means the reaction is endothermic. Heat is entering the reaction. Okay, here's what we call an energy diagram. On the y-axis, we have energy. On the x-axis, we have what's called a reaction coordinate. It's just how the reaction proceeds. And you would have a measure of the total energy of the reactants and a total energy of the products. Now, just looking at this, does it look like we're adding energy to the reactants to get to this level right here? Or are we taking away energy from the reactants? Hopefully you'll see we're starting here and then we're ending up here. So we have to add energy to the system. If we have to add energy, that means the reaction is endothermic. Endothermic. And notice delta H would be Remember, it's the sum of the heats of formation of the products minus the sum of the heat of formation of the reactants. So if we look at products minus reactants, do you see we have a bigger number minus a smaller number? So delta H would be a big number minus a smaller number. And hopefully, you see that that would be greater than 0. So for an endothermic reaction, delta H is greater than 0. So you need to just, if you see you're given a heat of reaction and you know it's positive, that means the reaction is endothermic. Let's look at another graph here. In this situation, we've got our y-axis for energy. There's energy right there. And we have our reactants and our products. This time the reactants start out higher than the products. So are the reactants giving off or taking in energy? Hopefully you can see that the reactants are giving off this amount of energy because the amount of energy is going down. So energy is given off. Is that exo or endothermic? Look back at those previous notes. This would be exothermic, an exothermic reaction. And let's look at what the sign of delta H should be. So we have the products minus the reactants, that equation from the first page. But if we just look at our levels, the products are smaller, they're at a lower number than the reactants. So we have small number minus a large number. And hopefully you recognize if you have a small number minus a large number, the result would be less than 0. So when delta H is less than 0, the reaction is exothermic. So let's do a quick summary of this. And here we go. So if the sign of delta H is positive, the reaction is endothermic. If the sign of delta H is negative, the reaction is exothermic. So what do we use enthalpy for? Well, turns out if you're given a reaction like this one right here, and you're given the enthalpy for that reaction, that's given to you right here. You can calculate things like how much energy you need to make something happen, or how many grams of something would have to react in order to make a certain amount of energy. So let's say you want to figure out how much gasoline do you need to produce a certain amount of energy to make your car go. You could use these equations. And we can use enthalpy the same way we do stoichiometry. We can use enthalpy in stoichiometry problems. So this value for the enthalpy right here, we could say is equivalent to 6 moles of water, or 4 moles of NO2, or 7 moles of oxygen, or 4 moles of ammonia. So negative 1396 kilojoules is equivalent in this reaction to 6 moles of water, or 4 moles of NO2, or 7 moles of oxygen, or 4 moles of ammonia. So when we do gram to gram, use molar mass, moles to moles, use the reaction coefficients. We can do moles to kilojoules, use the reaction coefficients, and delta H. Doesn't quite fit into the song, so we can't do it that way. But you want to think of it as 6 moles of water is equal to negative 1396 kilojoules for this reaction. We could do that with any chemical in the reaction. So now we can solve these A and B problems using those chemical equivalencies. But before we do that, let's just quickly do a shout out. Is this reaction exo or endothermic? Look at the sign of delta H, whether it's positive or negative, greater or less than 0. And the reaction is, drumroll please, exothermic. Okay, hope you're laughing. Maybe not. Let's do problem A. So, we're given 34 grams of ammonia. And whenever we have grams, we always go to moles. 17.04 grams of ammonia, NH3, to 1 mole of ammonia. This reaction, okay, we're asking how much heat is released. We're trying to get to heat. We're at moles, and we want to go to heat. So I can look at the 4 moles of ammonia. 4 moles of ammonia are chemically equivalent to negative 1396 kilojoules of heat. That comes out to be negative 698 kilojoules, but now we have to think about our signs. The question asked how much heat is released. When we release heat, we release a positive amount of heat. So our final answer is actually positive 698 kilojoules, because the question was how much heat is released. The question was not what is the change in enthalpy. This would be the change in enthalpy for the 34 grams. But that's not what the question asked for. It asked for heat released. How much heat is released? Oh, and now we have to look at sig figs. I can only keep 2 sig figs, so I would write this as 7.0 times 10 to the 2 kilojoules. And that would be my answer. Let's go on to the second problem. B. We have 2792 kilojoules of heat produced, and we want to know what mass of NO2 was produced. Now, here we're talking about heat being produced, and that's a positive quantity. So when we convert kilojoules to moles, we're going to take the absolute value of the heat. So we're at kilojoules, and we say, how can I get from kilojoules to something else? We look at our reaction. And we see right here, we've got kilojoules right here. What are we trying to get to? We're trying to get to NO2. And here's our NO2 right here. And we see we have 4 moles of NO2 and 1396 kilojoules of heat. So let's put that, whoa. 1396 kilojoules of heat is chemically equivalent to, I believe it was 4 moles of NO2. 4 moles of NO2. And we are asked for the mass of NO2. So we can't stop at the moles. We have to go moles back to grams, and there's 32, 42, 46.01 grams of NO2 in a mole of NO2. We get 368 grams of NO2. Why did I put on that 0.0 there? Hopefully you see we've got 4 sig figs. So we need to keep 4 sig figs. All right, moving on. We are now ready to look at coupling calorimetry with heat of reaction delta H. So I had to introduce you to what this enthalpy delta H was and talk about heats of reaction. And now we're going to learn about coupling heats of reaction with calorimetry. So when we have a reaction occurring in a calorimeter, but remember before we had Q1 is negative Q2. Now we'll think qcal, that's like our Q1. qcal is negative Q reaction, where Q reaction, right here, it's for the amount of chemical reacted. It's not necessarily the complete heat of reaction, delta H, because if a reaction has 4 moles reacting but only 2 grams react, well, 2 grams doesn't equal 4 moles. So Q is for the amount that reacted, for the amount, not necessarily the same number of moles as in the actual reaction. And that's why we use the symbol Q, heat flow. The qcal is just like our old way that we calculated things, ms delta T, for the calorimeter. And the calorimeter will have water usually and some reactants in it. So the mass for the calorimeter would be the water in the calorimeter plus the mass of any reactants in the calorimeter. Okay, now the Q reaction does not, we don't use an MS delta T for Q reaction. Q reaction is like this right here for letter A. If 34 grams react, how much heat is released? That would be a Q. So this 698 kilojoules, that would be a Q reaction because this 34 grams of NH3 is not 4 moles. 4 moles makes delta H. 34 grams only makes the 698, or with our sig figs, 700 kilojoules. So let's do some problems. So here's our problem. We've got 100 milliliters of 0.5 molar HCl. We mix it with 100 milliliters of 0.5 molar NaOH. It's in a calorimeter. We're given the initial temperatures of the solutions. We're given the final temperature of the solution. And we want the heat change for this reaction. So there's a couple things you need to know here, and I'll mark those in red. 1 milliliter of water is 1 gram of water. So the density of water is a gram per mil. That's what we'll be using for all of these problems. Whenever we are given milliliters of water, we'll always assume a milliliter is a gram for water. And let's put the information under each chemical. So we have, let's see, the HCl. We've got 100 milliliters, which is 100 grams of, oh, actually, let's start with the milliliters because we're going to need to use that to do a mole calculation. So we've got our 100 milliliters of 0.5 molar HCl, and we've got 100 milliliters of 0.5 molar NaOH. Okay, and then we have some other information. What we want to realize here is we're going to have to use our equation qcal is negative Q reaction. And we're going to have our data for qcal on one side and for Q reaction on the other. What do we know about the calorimeter? We know that TI is 22.5 degrees Celsius, and we know our final temperature as well, 25.86 degrees Celsius. Okay, so we know our initial and our final temperatures. Oh, I know the heat capacity of water. We've seen that often. It's 4.18 joules per gram degrees Celsius. Now, I actually do know the mass that's in the calorimeter. We have 100 milliliters of one solution and 100 milliliters of another solution. So we know we have 200 milliliters times 1 gram per milliliter. So we have 200 grams total in the calorimeter. So I've got everything to calculate qcal. Now, Q reaction, I don't know. What do we know about the reaction? We just know how much of each reacted. So we'll get there in a minute. First, let's just calculate qcal. So qcal is ms delta T of the calorimeter. And if you want to pause this and do it on your own, that's fine. That would be 200 grams, 4.18 joules per gram degrees Celsius. Final minus initial, 25.86 Celsius minus 22.5 degrees Celsius. When we calculate that all out, we get 2810 joules. Okay, so now we have to go back to our original equation. qcal is negative Q reaction. So I now know that Q reaction is negative qcal, so I have to change the sign here. So I know Q reaction is negative 2810 joules. Then I have to look at, what is this question asking me? I know that whatever reacted, it made 2,810 joules. And the reaction, we want to know, find the heat change for the reaction. We're trying to find delta H for this reaction right here. Now, let's look. What else do we know about this reaction? We know how much of each of these reacted. We could calculate the moles. So we know that 100 milliliters is 0.1 liters. And I have molarity, so I can get to moles. 0.5 moles per liter. So I've got 0.05 moles of NaOH. And if we look carefully, the HCl, same exact numbers. And I also have 0.05 moles of HCl. I don't have a limiting reactant because notice the moles are the same and the moles are the same here as well. So there's no limiting reactant. But what I've learned is that 0.05 moles of NaOH makes negative 2810 joules. Okay, so in my reaction, I don't have 0.05 moles. I have 2 moles. So here we just set up a ratio. All right, we're going to set up a ratio here. I'm going to do it at the bottom over here. So I have 0.05 moles is to 2810 joules as, now I use the reaction coefficient 2, as 2 moles is to delta H for the reaction. Okay, so I want to make sure you see what I did here. I just created a ratio. So I knew that 0.05 moles made was to negative 2810 joules. And I want to find out for the reaction number of moles. This is the reaction number of moles. What would delta H be? Because delta H goes with the reaction number of moles. So I just set up a ratio. The number of moles reacted is to the heat reacted. So moles reacted is to heat made or created, as the reaction number of moles is to delta H reaction. And now this is just a mathematical equation where I can move things around, and we can solve delta H is going to be, has to go on top, 2 moles over 0.05 moles times negative 2810 joules. That comes out to negative 112,400 joules. Now we got to check our sig figs. Let's see, when we did this subtraction right here, we got only 3 sig figs. Yes, we could keep only 3 sig figs there. And in the other parts of the problem, we've got, we've got 3 sig figs everywhere. So it looks like we can keep 3 sig figs in our answer. Oops, a little too high there. So negative 112,000 joules. Or if we convert that to kilojoules, you don't have to because I didn't ask for it. But hopefully you could see that would be negative 112 kilojoules. That's the answer for that one. Let's do another problem. Okay. We've got 3.53 grams of ammonium nitrate. We add that to 80 mils of water and a coffee cup calorimeter. Oh, I see a calorimeter. So we go qcal. We've got a reaction right over here. We see there's a reaction. Is negative Q reaction. And we're given all this information. So let's set up our little table here. qcal. What do we have? We have our T initial, 21.6 degrees Celsius. Our T final, 18.1 degrees Celsius. We want to find delta H reaction. Oh, I've got 80 mils of water. So now I have to be careful. My 80 milliliters of water would be 80 grams of water. But I have to look at what's the total mass in my calorimeter. I've got this ammonium nitrate along with the 80 mils of water in the calorimeter. So the total mass in the calorimeter would be my 80 grams plus my 3.53 grams of the ammonium nitrate. That's all in the calorimeter together. So I've got another 3.53 grams plus 80 grams. It was 80.0. So I have 83.53 grams in my calorimeter. And I can really only keep that up to the tenths place, but for now we'll just keep the sig figs and round at the very end. So, oh, and I know S. We're going to always assume S is 4.18 joules per gram degrees Celsius, even if we have a solution. This is mostly water. Most of the sample, over 90% of the sample is water, so we're going to use a specific heat capacity of water for qcal. And Q reaction, I don't know much about it yet. All I know is that I had 3.53 grams of ammonium nitrate. That's all I know for now. So, first step is to calculate qcal. qcal is ms delta T of the calorimeter, which is 83.53 grams, 4.18 joules. If you want to pause, go ahead, and you can solve this on your own. T final minus T initial, 18.1 degrees Celsius minus 21.6 degrees Celsius. Whoops, forgot the Celsius. Okay, that equals negative 1221.6 joules. So, I know from the equation right here that qcal is negative Q reaction. I just calculated my qcal. That means my Q reaction is the reverse or the opposite of this. So my Q reaction is 1221.6 joules. So I know 3.53 grams uses, actually, it's going to be an endothermic reaction, uses 1221.6 joules. I'm not going to worry about sig figs till the very end. So I need, for my reaction, I have to find out what would delta H be for 2 moles. Well, I've got grams here. In my reaction, I'm dealing with moles. So what do you think I have to do? I have to turn my grams into moles. So let's calculate what this would be for moles. So I have my 3.53 grams of ammonium nitrate. And that is 0.0441 moles of ammonium nitrate. And we don't have any more space over there, so we'll solve the rest of this problem under here. Now we're going to set up a ratio. We know that this 0.0441 moles uses 1221.6 joules. So the 0.0441 moles of ammonium nitrate is to 1221.6 joules as, and now we're going to look at our reaction. Our reaction coefficient is 2, right here, as 2 is to delta H reaction. So we're just making a ratio of moles used to the Q reaction as the moles in the reaction is to delta H reaction. And then we'll solve this. Delta H reaction is, let's see, 2 moles, I forgot to write moles here, over 0.0441 moles times 1221.6 joules, and we We get 55,401 joules, but now let's check our sig figs. You'll see in this piece right here, we drop down to having only 2 sig figs, because when we subtract the 18.1 minus 21.6, we get a number that has the ones place and the tens place, only 2 sig figs. So I can only keep 2 sig figs here, 55,000 joules or 55 kilojoules, and that is delta H for the reaction. And we are done. By the way, for now, don't worry about the little knots in there. This little 0 that we put for delta H, we put a little knot there. We will just always assume for this class that we are at standard conditions. So if we don't have the little knot showing there, we'll assume it's there for now. And that's all.